Hello there, math and tennis fans. Today I made this tennis court, and I made it so a ball can move. This is going to be a little playground I play with as I think about tennis and math projects. But I realized as I work on this today that this will be a real big project. I've been thinking about tennis and math for many years. In 2015, I did some research on it and how much different spins affect where the ball lands. This was one of the graphics I made, but I never could figure out quite how accurate this was. And I decided I'm just going to make a video on what I've done and hope that one of my students wants to pick this up as a senior project, or one of the graduate students wants to do research on it. In 2015, I just didn't have time to take it further. I was still teaching 500 students a quarter, as I always am. And I realized this week, as I started thinking about this again, I don't have time for this. But I think it's interesting. I'm certain that people have done research on this. But I think it would be fun to do some experiments. And this is a wonderful example of some of the uses of 3D calculus. I have many students right now that are jumping into Math 126, which is Calculus 3. And I'm hearing them grumbling about they're about to enter this discussion of 3D curves. And my hope is the next time I teach this, which is next quarter, I will refer to this video and take it further. So this is also a plug for my 3D calculus course. So if you take my 3D calculus course, you will see things you can click in there. I taught this during the pandemic for 2 years. I think I have some of the best visuals in the world. I'm probably going to teach it this summer. The department wants me to teach in the summer because they're hoping enrollment is high. And they said they'll pay me a little more if I can get lots of people to sign up. So this is a shameless plug. Okay, so anyways, some cool things we do in that course is we talk about how to study the motion along a curve. We talk about the tangent, which is that red vector. We talk about the inward pointing normal, which is the purple vector. And we talked about the binormal. And those are things, when I'm doing it, people are like, oh, vectors, what the heck is all this? When you actually study something in 3D, those things really matter. Okay? So Math 126 is not necessarily fun. You're going to do a bunch of calculation, but those tools are useful. Little thing I want to say is I have played tennis. I played tennis in college. I was the top player on a Division III school. Yeah, I know, just Division III. During the pandemic, I did slow motions of my shots. If you want, you can. I'm not going to show these right now. If you want to see them, you got to tell me in the comments that you want to see the fat guy. My belly pops out when I serve, which is disgusting. But I have a big serve. I used to be able to serve 120 miles an hour. I think now it's much slower, but I still tell people 120. There's my forehand. There's my one-hand backhand. Here's me hitting between my legs and around my back. During the pandemic, I made a bunch of videos for my family. I kept jumping the fence at the school next door that was closed, and I'd go hit against the wall because we couldn't play. So I have a lot of videos of things like that. So if you want a lesson on a forehand or a backhand or something, I can show you how to hit it badly like I do. But the real goal here is to present what I did and tell you some of the questions I want to ask, and I hope that a student will take this up. Okay? And then we get to play around with this a little more, which would be fun. Okay, so the research I did was on different spin angles. So I said, let's pretend we're standing at this edge of the court. It's 78 feet long. Here's the net in the middle. It's 3 feet tall in the middle. And this is also, I'm going to share this with my tennis people, and you get to tell me all the things I did wrong and all the dumb things I said and how ugly I look, which is what my tennis friends say. They are not very nice to me. Okay. So we're going to hit the ball 80 miles an hour. I just picked one. We're going to hit it at 10 degrees. And you can see if you don't hit any spin, it's going to go out by a lot. That's this blue curve. If you hit with 1,000 RPMs, and that seems weird, RPMs, but you know, it doesn't actually spin for a minute. But it's what the pace is. And this is actually reasonable numbers. Just from me, I'll show you some of the stuff I have in a second. So there's the green one, still going to be out. If you hit it with twice as much spin, it will land in. And 3 times as much spin. You get a lot more margin of error if you hit topspin. It is dramatic. So those people that haven't played tennis don't know this. Topspin is dramatic. in ability to, you can hit the ball much higher, it still goes in, you can hit the ball harder. It has this incredible effect. Also, the way it bounces is a little different. What's interesting is if you hit backspin, you can make it bounce backwards. And we're always thrilled, which happens very rarely, when we hit a ball over the net and it bounces back over. We're trying to do it all the time, and it almost never happens. And when it does, there's this rule that says it's one of the few times that the person on the other side of the net could actually reach over to hit the ball, but they can't touch the net. Again, that almost never happens, but we're hoping, crossing our fingers. Okay, so a little bit of background, and then I will explain how I got that, and then I hope you'll take this project further. Okay, so I had this book, Physics of Tennis. I'm going to this is the same guy, Rod Cross from University of Sydney. I don't know him at all, but I thank you for all the work you did. You published a huge book based off of lots of research. It appears Tennis Warehouse found you and had you publish some of your things here. So if you want to have some official stuff that's not for me, go to Tennis Warehouse. They have this Tennis Academy. It's a little sad because they added a pickleball version. I like pickleball, but I don't like the pickleballers taking my court. This is a chapter from his book. This is the book I got from him years ago, so a little plug for Physics of Tennis. It's a huge, fat book, mostly about like the technology of rackets and other things. But he goes through and talks about the different forces, and this is what I will talk about briefly in terms of math here in a second. Tennis Warehouse has these little trajectories. They have different, versions of this and different numbers. So I've compared a little bit with that, and my data seems similar. But if students that have had me as a teacher know how much I emphasize checking our work, because I don't want to present something that's wrong. And I don't like that I can't officially check my work. So this is not up to my standards, but anyways, I thought it was interesting to see what AI said. It's pretty close. It gave this equation at the end, but I feel like it's simplifying. It doesn't tell the reader that they're simplifying here. So there's a simplification right here. So I think the last step is actually wrong. This is always something to be careful about, especially with math and AI. You have to think critically about what it shows you. Okay, so let's talk about this. And I'm no expert on these pieces, but what I'm going to do now is come back here and just talk about this idea. I don't know a ton of physics, but I feel like calculus has helped me better understand the ideas we're going for. I did several, at the time, the person who I was playing with, what I was sharing these things. So we were trying to come up with questions. So that was the first one, which I thought was kind of cool. The second one is I did a bunch of analysis on things like this, where I said, I'll pull this up and talk about this in just a second. But I was like, well, what if you hit a ball 60 miles per hour and it's flat? What's the lowest angle where it will clear the net? And that was 5.75 degrees. What's the highest angle where it will stay in? That's 11.25 degrees, and then halfway in between. And so I did that with each one, and then I did it with spin. And the thing to note here, I was just trying to quantify this, that there's about 6 degrees here, a little less than 6, that you can hit within, and the ball will go in. And here there's 13.25 degrees. So that's the margin of error piece of it. I was trying to get some measure on the margin of error, so I thought that was sort of interesting that you do notice with spin, you have to hit it at a higher angle. That's because the spin brings it down. And usually when people are first learning to hit topspin, they hit like the first 5 or 6 balls in the net because they're using too low of an angle. So as soon as you get lots of topspin, you got to hit it up. And really the rule in tennis when you're first learning is you always have to hit it up. It's kind of, for some people it's counterintuitive because there's that net there. They think that they can just hit it straight. You got to hit it up. At least 10 to 25 degrees if you can hit with lots of spin. Okay, so I thought those were interesting little facts, but I couldn't verify the accuracy. Okay, I was just using kind of what I knew from years of experience playing tennis. How does someone get such a thing. So then I will show you a little bit of the code and what I did. So the principles don't require a whole bunch of understanding. It's this one idea, they call this Newton's second law, that the way in which an object accelerates. I'm going to do it in 3D. Really, this is like 3 components. This is the X, Y, and Z component of acceleration. I probably lost some of you already, but we're going to stick with me for a second. What you're trying to do is the sum of the forces. And this is what they do in physics, is they say, we're going to study the forces. You're going to do a whole bunch of labs, and so you know what they are. And then that accelerates something. Okay, so the 3 forces, and I'll take you through this, and I knew nothing of this. So this is a total, mostly what I'll show you is a total moron like me was able to make these pictures, probably inaccurately. So what did I do? I just took out this book, and I went, okay, there's gravity. Now, of course, I have studied gravity before, and the force due to gravity. It only affects the Z component. Let me do this first before I jump into math here. There's the force due to gravity. There's the force due to what we call drag or air resistance. And then there's the force due to the rotation. That's called the Magnus force. So those are the 3 forces we're going to account for. Now, always with these things, you can add more and more pieces in, but people have studied each of these really carefully. The force due to gravity just acts downward, and it's mass times the gravity constant. So that part we know. What we're building up is what's called a differential equation. And this is, unfortunately, something we can't do a lot of in Math 126 because we haven't studied differential equations in detail. But the acceleration is the second derivative, the velocity is the first derivative. Once you can get all of this written out, you can put it into a solver and have it graph, which is what I did. So I didn't do anything clever. I just copied down what the book said. Okay, so then I said, what was the next thing he said? Okay, there's gravity, yes, and then drag force. And he said drag force was this. So drag force was, and if you study drag, and I wish I knew more about this. I did not take much physics. I was a number theorist, cryptography person, and I feel bad all the time because then I started teaching students and I realized no one cares about the theory. The majority of students want the application. And so as a teacher, I have learned applications in order for students to want to be listen to me. So what's written here is it's dependent on the velocity. And if you've never studied that before, if you stick your hand out the window of your car and you're going faster, your hand gets pushed harder. People know that. Right? If you're on a roller coaster and it's going fast, your face is being pushed harder by the wind. So the normal model, which we did in Math 125, is proportional to velocity. But for certain objects, it changes a little bit for how it relates to velocity. So in general, drag is a function, some function of velocity, how fast you are going. Turns out for a tennis ball, Rod Cross here, the Professor Rod Cross says, the square of the velocity seems pretty good. The drag force is proportional to the ball speed squared. It has this formula, where each of these things have different meaning. This is the drag constant. So if you study things moving through the air, this seems like a lot, and it is a lot, but it's actually not so bad. I went through piece by piece and did this in 2015. I just didn't keep very good notes, and I don't want to do it again. D is the density of air. All of these are like known numbers, and so you just plop them in. Now, I was trying to do everything in feet because that's the dimensions of a tennis court, and so I had to convert all these numbers. So I went through and converted all these numbers, and I had something, the velocity squared. When I did those pictures, I was doing everything in 2D, not a true 3D discussion. When I, according to the the discussion here, if you want to go in full 3D, and this is where I was trying to figure this out, they say that you need to do v times and so this was the part I don't think is quite valid, how you do the velocity speed. Now you could change it to the velocity, but then it's not as good of a model. So this is the part that I was having trouble with. I saw in one place that you maybe could multiply times the speed. So there's a place I'm stuck. Now when I did this before, I just did it in 2D, which simplified things quite a bit. Because then I could just say the speed squared, which is the square root of x prime squared plus y prime squared. Here I need a vector. Okay. So that's the part I'm leaving to my students to do the full 3D model and to get it in some sort of form that I can then plot it. Some sort of estimate that I can plot it. Or maybe you can write a program to help me do that. Okay, so you have that piece, and then you have the Magnus effect. Sounds like a chess player. So here we have plus the magnitude of the Magnus force on the tennis ball is given by this. So then they say this is 1/2 CL. And I should say the force due to drag is going to be the opposite direction of velocity. So this is then area times d. This is the area of the object moving through the air. And so you take the radius of a tennis ball. D was... What did we say D was? I've forgotten. Oh, it's the air density. And then it says there's going to be a 1/2, and it's the velocity squared again. Now, how we deal with the velocity squared, maybe I'll just leave it like that for a second for my physics students to set it up in a 3D form. Okay. And then there's some more talk about how you should adjust it for the spin. And then you see these force diagrams. So I need an expert to tell me exactly how do I set this up. I'm showing you I'm not that smart. Once we have it all together, whatever we're going to say, then we have a differential equation. So they give an example here. So basically they separate the three pieces. You would set this first component equal to the first components of the other one, and the second component and the third component you would solve. The challenge with solving is you have second derivatives, first derivatives, and so you need some numerical method to graph it. But there are systems that will do that nicely. And notice a few things. It will involve the way in which the ball is rotating. There's lots of interesting things to talk about here. You have this tennis ball, and maybe it's going this way. The air resistance is against it. Maybe it's spinning a certain way. And it turns out that there's this vector that sticks out of it, which is the axis of rotation. And so you would need that information, and that's where the spinning goes. That's this omega. For my Math 126 students, you're seeing some of these operations, cross products. Being able to study those vectors are going to go back to these ideas of which direction am I going? What's a vector that points inward? What's a vector that points up? So in this analysis, the stuff you're doing in Math 126 will be valuable. I think it would be, it's hard enough as is, but if you didn't take Math 126, it's very hard. Okay, so what I did is I did that in 2D, which made things quite a bit simpler. All right, I think that's all I will say on that piece. So my official notes here, but that's just a proof of idea. And that's what you've been doing in Calculus 1 and Calculus 2 and Calculus 3, is you've been saying mass times acceleration is the forces. It's just you first did it in one direction, which is what I did with like throwing my tennis ball straight up. And in that case, you could just think of just one component. M times x double prime was negative mg. And that's just an object going up and down. And that's it. So we have x double prime is negative 32. We have x prime is negative 32t plus a constant. And this is the stuff you do in Calculus 2. And that's similar to what you're going to do with more variables. Okay. So anyways, I did that. I did a bunch of different ones. I did 60 miles an hour. 60 miles an hour, it hits the net when you go 10 degrees. So it's not hard enough. When you have lots of spin. 4,000 RPM is kind of the biggest it gets. 80 miles an hour, 10 degrees. We already looked at that one. And then I did a few other ones. 60 miles an hour, 8 degrees. With backspin. Now backspin is going to make the ball actually go further. So it's nice to kind of compare the 60 miles an hour with topspin and backspin, and realize the ball goes much further in terms of where it lands. Here's 80 miles per hour with backspin. If you hit it really hard with backspin, it's hard to get it to go in. In fact, you can only do it at a very low angle. This 4 degrees, the reason I picked 4 degrees is the only one of these that went in was the blue one that didn't have any spin, and then you basically hit it flat. So you have to hit it really low. I tend to have a pretty good forehand slice when I'm in trouble, but I have to hit it really low for it to go in. Other things I was going to say there. So the other analysis I did was this one with this margin of error being, you're about a 13 degree range you can hit it in if you hit with lots of spin, as opposed to about a 5 or 6 degree range. So I thought that's something, provided my results are correct. The actual work was this. I don't know if I'm capable of this anymore. I used to be much smarter. I've lost so many brain cells in teaching thousands and thousands of students. I've given them my brain cells. Anyways, the comment here is this. So that differential equation I have written out, I typed it in. Now this looks like a terrible mess. In fact, I had to look at it a while today before I remembered what I did, because I didn't keep very good notes. But you can see I have the only important part is right here. And a lot of it's pieces, but there's x double prime, and these are all those numbers, like this 0.003 I think was the radius of a tennis ball in inches or feet or something, can't remember. Here's the velocity. Today I was trying to add z prime. So this was, the omega was how fast it was spinning. And so I had to do a bunch of little plugging in. Once I got it in there, I asked Mathematica to solve it, which means it just gives me a curve, like a numerical solution of a curve. And then I had to do some things to flush it out a little bit. And then I made this. I had this intention of making like an animated 3D things that people could interact with. And I did it. I was successful. And then when I was done, after all that work, I realized in order for someone to be able to use this, they had to download the Wolfram Alpha player. And I found out that that's kind of a pain to download. And even once you download it, it runs really slow. And so I discovered it was a huge waste of time. I was going to show you it during this video, but I realized it's so slow in processing that when I move a little one of these sliding bars, the video stops recording very well because everything slows down. But there's an example. I do have this. I would love a student to make a better version of it. I can give you the code. I just need someone that's better at coding that can make this run quickly. But there it is. The initial height is 3. And I'd like to do this in 3D as well. It crosses the net at point. So I had a bunch of data I did. It hits the ground in 0.87. It's in. Cool. So once I had that, that's when I started asking my more general questions. Okay. This work over here was just me playing around with it today. So there you go. There's my analysis of tennis balls. I think there's some interesting facts there. I think the principles are right. The precision of my curves is what I'm unsure about. So I'm not going to vouch for these numbers as being absolutely correct, because I would need someone who's more of an expert on these sorts of models. But I think there's some validity here, which is there's that margin for error that you get for hitting quite a bit more spin. I would like people to reply in the comments of other questions. I have an extremely long list of questions I would like to ask about tennis. I would definitely like to talk about how the ball hits the ground and bounces. Tennis Warehouse does a little bit of that, but I would like to be able to get a model that would accurately have the ball bounce and go back over the net, because I'd like to make an animation of that, and I'd like to match it up with what we see. Interesting other things. I have a bunch of things. How it bounces, the angle, if it spins, when it slides, what angles you can hit to get the ball in. We can talk about the sweet spot and balance points and where you put the weight to get various different swing points. I can tell you how those are calculated. There's too many questions to ask. That's where I'm stuck. Okay, last little piece of this is that I did notice a few little things that I liked when I was reading this about the drag force. He says that a serve loses about 75% of its speed from when it is struck to when it hits the ground. So that's a pretty interesting fact I'd like to dig into a little deeper, which is drag is, because you're hitting the serve so hard, the drag on the tennis ball is really high initially. So a serve, even though you might say a serve is 150 miles an hour, when it crosses the net, it's going much slower. And when it hits the ground, it's going much slower. And after it bounces, it's going much slower. So it's not like it gets to the receiver's racket at 150 miles an hour. It's still hard to return it. But there we go. So some good information in here to my friends that laughed at me when I showed them this book. But that mostly just gives an example of how an idiot like me was able to make those pictures by just using the principles I learned in Math 126 in teaching it. Mass times acceleration is the sum of the forces. I just had to copy down the force formulas. There was a lot of work in getting the numbers right and converted, but that's pretty cool. Maybe we'll end this with one of the videos, maybe two. Here's me serving. Here's the big guy serving. There's a 120 mile an hour serve. There's my belly coming out. All right, and then here is an idiot hitting the ball behind his back. That was the end of the video and I messed up. Oh boy. Who plays tennis in jeans? What's wrong with that guy? This is my son recording when he was really little during the pandemic. So that's why the video quality is so high. All right. Hope one of you comes up with some things here and can work on this maybe over the summer with me. It would be lovely to continue this project that I never finished.